thank you for coming, those of you that come. I want to, first of all, apologize for not speaking any Russian. I've given these talks many times in China, and I still only know 4 words of Chinese. This is my first time in Russia, and I currently know 0 words of Russian, except maybe da and niet, maybe. So I have to give this talk entirely in English, but apparently there is simultaneous translation available if you get a headset, and that will probably help as far as understanding. So this is probably what most people think of when they think of the periodic table. In Russia, maybe it looks like this, or maybe even sometimes like this. This is closer to Mendeleev's original formulation of the periodic table. All of these versions have one thing in common, which is that they're just numbers and letters, just, you know, words on the paper. And students are expected to memorize these words or these letters. Maybe they memorize 20 elements. What are these symbols and the atomic number and the atomic weight? But what does that tell you? What the name of an element doesn't tell you anything at all about the element. It's just a name. This is really not what the periodic table is about. This is, I think, a real periodic table. So we can turn this off. Can we make those go off too? There we go. OK. So this, I think, is what the periodic table really is. It's a table of real things, real physical substances. Every element is something particular. It's solid or a liquid. It's cheap or expensive. It's dangerous or safe, light or heavy. Every element has some important role to play in the world. And if you want to learn something about the periodic table, you need to learn about those elements as real things, not just numbers and names. So I want to tell you first a bit about where this video came from. If you think about it, like, how was this video created? To do this, I had to gather physical samples of every one of the elements, photograph them on a turntable, and then do a lot of processing. So why did I do that? How did I do that? Let me just tell you a bit about how that was done. So it started with a misunderstanding, actually, a book that I was reading, a book, Uncle Tungsten by Oliver Sacks. It's a wonderful book. I highly recommend it. I'm sure it's available in Russian. He talks about visiting a periodic table in the Kensington Science Museum in London during the Second World War. And you have to understand that in English, the word table can mean 2 things. It could mean a grid of numbers and letters, sort of like a periodic table. But the same word can also mean a table like this that you sit at. Maybe you have dinner at it. So when I read the sentence in his book, I thought he was talking about a table that was built in the shape of the periodic table, because the 2 words mean the same thing, and the way he wrote it, it sounded like that's what he meant. And I thought that was a wonderful idea. Like, that's a great idea. One should make a periodic table. And then I read a little bit further in the book, and it turns out that's not what he meant at all. It's actually a periodic table display on the wall in this museum, same as every other periodic table. And I was very disappointed to find out that they had not, in fact, built a periodic table, a joke which works only in English. But so, of course, I had to make one. So you see, in English, this is an inherently funny object. I'm sorry, it doesn't work in Russian. But, you know, this is a joke. Like, just by this physical object itself is a joke. It's a periodic table. And I thought, you know, this thing should exist in the world, so I built one. And then I thought, you know, I should continue on the misunderstanding that Oliver Sacks' book had instilled in me, of the idea that there was a periodic table that had elements on it, so you could see where each one went. So I started collecting elements to put on this table. And then I just kept going, and I had more and more of these elements. And then eventually they didn't fit on the table. I had to get more cabinets. And then after a while, Oliver Sacks actually came to visit this table that his book had inspired. It was a great honor to have this great author, very famous author, come to my office to see this periodic table that his confusing sentence had inspired. So that was cool. And then, so this is another play on words. The Nobel Prize, maybe we'll unplug this. The Nobel Prize is a very, very important, serious prize. I don't have a Nobel Prize. But there's another prize called the Ig Nobel Prize, which it has a name in Russian. I'm trying to remember what the name in Russian is. Was that? Schnobel Prize, all right, Schnobel Prize, okay, yes, yes. So I won that in 2002 in the chemistry prize, which is in some ways much more difficult than winning a real Nobel Prize, because to win a real Nobel Prize, you just have to spend a lifetime doing important work in science. But to win one of these, you have to do something completely ridiculous. So that was great. And eventually, I had so many element samples, I thought I need to take pictures of each one and take pictures and describe them, or else I'll forget what each one is and where it came from. So I made a website where I have a little database, a catalog of all of these samples. And then I got a very surprising phone call. The editor-in-chief of Popular Science magazine called me. This is the largest circulation general interest science magazine in the US. And he asked if I would like to write a column every month about chemistry, which, I'd never written for a magazine before. I had no idea how to do that. But I thought, OK, I can do that. And I did it for 10 years, every month, a new column, which actually, where's my Tim, can you find the bag? Yeah. So I thought I'll try it. So for 10 years, every month, I did that. And eventually I moved my website to a better URL, periodictable.com, and made it look a little nicer. And once I had enough pictures, I thought I'll publish a poster, my own version. Right, so these are two, yes, these two books are actually collected columns from my Popular Science column, available in Russian now. So I thought I'd make a poster. Because I have enough pictures, I'll make my own periodic table poster that I think is nicer than the other ones. And it was very expensive to do a print run, but I made the money back in a week, so I thought that's a good business. So I thought I'll write a book. Because after a while, I had enough to say about each element, so I thought I'd write a book. That book has now been translated into 25 languages. It's sold something like 1.5 million copies. It is also available in Russian, along with its sequel molecules. And in fact, just yesterday, I found these in a bookstore. I don't remember the name of the bookstore, but maybe somebody can tell me what it was. So these are available here in Moscow in the bookstore. Basically, because of this misunderstanding. Like, the only reason I did all of those things was because Oliver Sacks had written a confusing sentence. So my book, it's not about sort of technical things in chemistry. It's about what I think is interesting about each element. So this is the page on nitrogen. You see it in pure liquid form, as you should. But you also see examples where nitrogen is found, like nitroglycerin pills for chest pain, or boron nitrate ceramics. The page in silicon. So again, there's a picture of a piece of silicon. But there's also a discussion about how maybe silicon could be the basis for another form of life. This is a common theme in science fiction. You could have silicon-based life because silicon is in the same column of the periodic table as carbon, and maybe that would be a reason why the chemistry is similar. I actually think it's much more likely that silicon-based artificial life will be artificial intelligence built on computers rather than chemical life. So that's discussed there. But you remember this video. So it's, in a print book like this, you can only see one picture. It doesn't move. What if you could have pages from this book, but where everything would move and you could see it from all sides? So I thought I really want to make that. Is Harry Potter familiar here? Does everybody know Harry Potter? I thought, what if Harry Potter had this book? He would be able to have these objects pop up, and he could look at them and turn them around. So I wanted to do that, but there was no way to do it. There was no practical technology for doing that. until the iPad. This book came out right before the iPad was released. And so as soon as the iPad was announced, I thought, this is the way I can make this book. And so we immediately worked on it and made an iPad version. So in the iPad version, you just take your finger. If this is what I'm giving the presentation from. You can spin these things with your finger. And this is the closest thing that I've ever experienced to making something magical. I thought, let's have Harry Potter's version of the book, and boom, there's a device, and now there's an app version of it, which, by the way, also is available and supports Russian as well. The other thing that we could do in the book, in the iPad version, which we couldn't do in the print version, is a theme song. And I'm going to play that for you now. Hopefully the sound will work. So this is a song recorded in 1959 by Tom Lehrer, who I traded an iPad for the rights to the song. And here we go. Here we go.
These are the only ones of which the news has come to Harvard, and there may be many others, but they haven't been discovered.
So, yeah, so you notice this was recorded in 1959, and since then, many elements have been discovered. If he was recording it now, the song would have to be much longer. And unfortunately, even this video was made several years ago. So 2 more Russian-named elements are not yet in this video. I have to make a new version. There's Moscovium and Oganesson, or however you pronounce that. I have no idea. That are not yet in this video because I haven't regenerated it yet. So that's the story of how I got into collecting elements. And now I want to tell you some stories about the elements themselves, because I really love elements. I think elements are very interesting. And I give these talks in many places, and very often people ask me, what is your favorite element? And sometimes I tell them, well, I don't have a favorite child either. I'm not going to tell you which of my children is the favorite, and I won't tell you which is my favorite element. But I do like titanium a lot, because it doesn't rust and because I have some very nice titanium things. But regardless of what the element is, there's always some reason to think it's interesting. So, for example, sodium. Sodium is a wonderful element. If you ever have some sodium, go find a lake and throw it into the lake. That's the thing that you do with sodium. This was a party that I had at my house, and we threw lots of sodium in the lake, and it was great. So that's why I like sodium. So this is what happens if you throw sodium in water. But imagine what would happen if you combined it with another very dangerous and highly reactive chemical, chlorine. So I think I'm going to unplug this. We don't need the sound. How do I make this keep playing? There we go. Yeah, so this is what happens if you take a pool of molten sodium metal and blow chlorine gas into it. Chlorine is an extremely dangerous, powerful gas. They react with each other quite vigorously. And what comes out the top is sodium chloride, which hopefully many of you recognize as table salt. The thing that you, yes, and here is the first disaster of my talk. So that was popcorn, which tastes better with salt on it. And sodium plus chlorine gives you table salt, like you eat. But unfortunately, I didn't take into account that the net that was holding up the popcorn was made of a plastic that would melt. And so the popcorn melted and dropped into the sodium, and the sodium immediately exploded, as one would expect. So you might think this was a disaster, and we had to do the whole thing over again. And it was quite dangerous to do this in the first place. But actually, this was perfect. We got, this is a page from the book, we got a beautiful picture, and then we got a much better picture when the disaster happened. This is, I think, one of the best pictures we've ever taken. Just by luck, it came out very nice when there was this disaster, and then you could see how powerful sodium is. So I like accidents when they happen in these things. And in fact, after that, I spent a lot of time trying to get even better sodium explosions using fancier cameras and high-speed flash and sound triggers. And I never got one that was quite as nice as that first one, just by accident. There's also, so lithium, the left-hand column of the periodic table, the alkali metals, is known for catching fire in water. Lithium normally doesn't. If you've ever seen demonstrations of dropping alkali metals in water, lithium usually just sits there and bubbles and does nothing. But it turns out if you use the lithium foil from a non-rechargeable AA battery, it has a very high surface area. It's sort of activated lithium foil, and it will actually explode. And this is some filming we did for a television show. We even got the ultimate for alkali metal water explosions. The best thing you can possibly do is to break the bowl it's in, because that's very dramatic. And I was surprised that we were actually able to break bowls with lithium. We wait a second here. Actually, this has sound, I think. Yes. So we managed to break the bowl with lithium, and then proceeded to do this over and over again with all the glass bowls we'd had, and broke them all to get the perfect glass breaking film. And here's another nice disaster. Worked out nicely. This was for a column on distillation, how alcohol is distilled. And soon we will see the disaster. The problem is here, this whole thing was set up to look right, not to actually work. It was never intended to actually be a distillation apparatus. In particular, that boiling flask is not a boiling flask, and it's not made of heat-resistant glass. So the whole thing fell apart. But the point is, we got the shot. And this is unretouched. That's exactly how it came out, no Photoshop. Because the whole setup was there to make the picture to put in the magazine and then in the book. So that was nice. This was another Photoshop. One of the things I think is important in what I do is always to try to explain not just what the chemistry is, not just what you're seeing happening, but why it matters to you and why you might want to learn about this or understand it. So hydrogen soap bubbles is a very common demonstration that you'll see. You blow hydrogen into soap bubbles, you run after it with a candle, and you light them. And then if you mix in, so this is pure hydrogen. I think we can plug this in. Yeah, so it's fairly gentle. It burns quite gently. But if you now mix in, yeah, so here comes slow motion there. It's taking quite a long time for the reaction to complete. But if you mix in, shortly here we will see, hopefully. Should probably cut this video a bit. Yeah, if you mix together hydrogen and oxygen first, and then light it, you get a much more powerful reaction, a much faster reaction. And this one actually scared me. The amount of gas building up in there, we finally had to cut it off. It eventually basically becomes like a bomb. And the reason this is interesting, I think, is that this explains why gas explosions happen sometimes. You think, the gas that you cook with, methane, natural gas, it usually burns very gently and safely. It's just a little flame when you cook with it. But every once in a while, it blows up an entire house. Or sometimes, actually recently in America, there was a disaster where a whole row of houses was blown up by the same gas. And the reason is that it burns gently, just like the hydrogen, when it has to mix with air as it's burning. But if you have a gas leak and it fills up the house without being lit, and then you light it, then you get a powerful explosion. And the hydrogen bubbles are a good demonstration of that and a good way of understanding why gas leaks are so dangerous. Because when you hear, this of a gas leak coming out, that's a bomb being built up. It's slowly constructing a bomb in the room that you're in. And you better do something about it, because if anything sets off the bomb, it can be incredibly dangerous. So I've done this demonstration, for example, on a crazy Japanese television show. But I don't really like doing it this way, because nobody really learns anything. It's just fun. But without the explanation of why this matters, it's sort of empty. So I told you I'd like titanium because it doesn't rust. Iron, on the other hand, it rusts. The fact that iron rusts is really a very miserable fact about chemistry. Iron is a wonderful metal. It's cheap. There's a huge amount of it. You can make all kinds of things out of it. But it rusts. And so every single iron thing in the world, every bridge, every car, every building, everything made out of iron is constantly rusting. The estimate is something like 70 trillion rubles, about $1 trillion per year of economic loss because of that chemical reaction of iron rusting. You can make it happen in an interesting way, but I think the best thing about rusting is the fact that it can be reversed. So rusting is iron becoming iron oxide, combining with oxygen from the air. If you take iron oxide, rust, and mix it with aluminum, you make a powder called thermite. And if you then light that, you get the thermite reaction, which is aluminum atoms stealing oxygen atoms off of iron oxide, giving you back iron metal, sort of unrusting the rust. And the aluminum binds the oxygen much more tightly, so there's a lot of energy released in that process. And the result is you get not just iron metal, but you get white-hot liquid iron, a tremendous amount of energy released. This is a demonstration of how that's used to weld together train tracks. You imagine you have two iron rails, and you need to fuse them together, not just sort of tack them together with a weld, but actually make them into a single piece of iron so that a high-speed train can go over the track very quickly. And this is one way that it's done. You set up a thermite pot with 10 kilograms or so of thermite in it. It drops the liquid iron down between the tracks, and it's so hot that it actually melts them together. And then after it's cooled and ground, you have a single continuous piece of iron with essentially no joint anymore. And the trains can go over that very quickly. So you have rusting and unrusting as a complementary process. And that's sort of a redeeming feature of rust, is you can do that to it. You can actually do it with titanium, too. So there's titanium oxide, essentially the rust of titanium, also reacting with aluminum and giving you titanium metal out. This also is a process that results in a lot of heat being produced. We chose these pots especially so that they would crack in an attractive way. And when you watch this one, when it cracks, you see there's this liquid running down. That's actually not mostly liquid titanium. It's actually liquid flower pot. The heat has melted the clay of the flower pot, and it's dripping down at a very high temperature. So elements are wonderful as individuals. I've written a whole book about them. But you can also assemble them together into molecules. So for example, here, if we start with hydrogen, the flammable gas we saw, carbon, coal, diamonds, hard substance, oxygen, highly reactive gas, and chlorine, very poisonous, toxic gas. What happens if we put these all together? Well, there's actually many millions of different things that you could get, different molecules you can get that combine those 4 elements. Some of them are poisonous, some of them are harmless, some of them are boring. Some of them taste really good. This is actually an extremely good tasting molecule. It's called sucralose, and it's a sugar substitute that's used in many kinds of sugar-free chocolates that I'm fond of. It's interesting that the properties of the elements are completely unrelated to the properties of the molecules that you can make out of them. That's interesting, so I ended up writing another book. After I wrote the elements book, I wrote another book, which now also available in Russian, Molecules, which then led me to writing another book called Reactions, which unfortunately is not yet available in Russian, but it's out in English last year. So I'll show you some examples from my reactions book. So this is a reaction which it's sort of frustrating because it's very beautiful. It's, I think, one of the most beautiful chemical reactions I've ever filmed, along with a disastrous sodium chloride. But I have not yet figured out what makes it relevant to sort of everyday life. This is a reaction between aluminum, metal, and bromine, forming aluminum bromide. This is a great chemical demonstration. It's often done in labs as a demonstration of this category of reaction. But I don't know what it has to do with anything explainable to the common person as to why this matters. And that's frustrating because I think that's very important when talking to chemistry to the public, to have some reason why they should care about it. I'm hoping that someday, somewhere during one of my lectures, somebody will come up, ask a question at the end and tell me, why is this reaction relevant to the world? But so far, not yet. So it was actually my first editor at Popular Science magazine who insisted that I always have some kind of explanation of what the relevance is. So this is a demonstration of the fact that diamonds are flammable. For a long time, the sort of slogan of the De Beers company was, "Diamonds are forever." I don't know if they use that in Russian or not, but diamonds are forever, they last forever. You should buy your girlfriend a big diamond because it will last forever. Well, this is nonsense. Diamonds are flammable. This is a diamond burning in oxygen, in liquid oxygen. You light it with a hydrogen torch, you drop it in liquid oxygen, it burns up. And in fact, in a hot house fire, like if your house burns down and you have a diamond wedding ring, and you find it afterwards in the ashes somewhere, you'll find a pool of gold and no diamond, because the diamond will be consumed in the fire. This, on the other hand, so the second example here, this is a cheap imitation diamond, a cubic zirconia, which is in fact pretty much indestructible. You can do almost anything you want to it. It's almost as hard as diamond, and it's completely impervious to heat. This is a hydrogen torch, is the hottest flame, the hottest chemical flame you can make. It melts the gold or whatever metal this ring is made of. But the cubic zirconia is untouched, unlike a diamond, which will burn up. So I like this demonstration as yet another reason why diamonds are kind of stupid and you should not buy them. So this is a demonstration of the wrong way of cooking a turkey. So we have a holiday every year at the end of Thanksgiving when we're supposed to cook a turkey. If you do it the wrong way, you provide a demonstration of the importance of surface area and flammability. So cooking oil, very hot cooking oil, can sit in a pot and it will not burn because the surface area at the top of the pot is very small and its interaction with oxygen in the air is limited. But if you drop a cold, wet turkey into it too quickly, it sprays up, boils out, and you have very fine droplets of oil spread out in the air. And the surface area is very high. And that will then burn, and it'll burn quite dramatically. And every year people burn their house down because they don't understand that this is not how you should cook the turkey. You have to thaw it first and dry it and put it in the oil slowly, not drop it the way that we did. This, of course, was not at all a disaster. This was absolutely what we intended to have happen, and it worked perfectly. So I think we'll take this off. So this is another, whoops, make it go? Nope. Here we go, right. So this is a demonstration of how often the fuel is not very important. So for example, the big rockets, the Saturn V moon rockets, all the big Russian rockets, the fuel in those rockets is kerosene, which is basically diesel fuel. It's the same fuel that trucks run on. The difference is that in the rockets, the kerosene is reacting with liquid oxygen. So it's not the fuel that matters, it's the oxygen source and the purity of the oxygen. So this is a cutting torch. It's cutting through steel. It's made entirely of pork, specifically Italian prosciutto. And pork will burn like a torch if you feed it with pure oxygen gas. So what's coming in the back there, there's no fuel, there's no acetylene, there's no hydrogen, there's no nothing. It's just oxygen. The only fuel is the pork. And so that's in the column describing the importance of oxygen in their burning reaction. Very often is not the fuel that matters, it's the oxygen. And then there's also the one made with breadsticks and a cucumber. So that one worked quite well also because the bread, the carbohydrate in the bread, is flammable. If you feed it with pure oxygen, you get a powerful flame. So I think if you remember the periodic tables that I showed earlier, these tables of numbers, many students come away with the feeling that chemistry is sort of boring and is just figures and formulas and it's not interesting. But that's, chemistry is the story of everything. Everything that happens in the world, everything that happens in you, life itself, is a chemical process. And I think it should be one of the most exciting subjects in school, not one of the most boring. So that I find chemistry very fascinating, and I hope that you also have been interested in chemistry and will continue to learn about it. And thank you for coming, and I'm told that I should leave room for questions, which we now have 15 minutes for questions, I guess. So. Yep.
Good evening or good day. My name is Philip. Mr. Gray, I'd like to thank you for your invitation and a wonderful presentation.
Welcome.
And one question is about your videos from the presentation. Did you make them by yourself?
Usually, so it depends on which videos. There's some of them, it was mostly myself, and I have a photographer that I work with, Nick Mann, who helped with most of those videos. Some of the ones that are, well, all the ones actually that are in the Mad Science books, the popular science column, the process was that every month a fairly good, prominent commercial photographer from Chicago would come down to my sort of compound, and we would work for a day doing a photo shoot and get pictures for the magazine. Basically, the magazine paid for this very good photographer to come and spend a day doing this to get pictures for the magazine, and we would take video at the same time. Those videos are usually not as good as the ones that we did especially. And then, some of them, like the lithium explosions, that was a television show, a Discovery Channel television show that we were working with. So they bring their crew for that. This video is entirely just me, and it's not a video. It's actually time-lapse, pictures rotated and then assembled programmatically.
And the second one is about rails. As I know, in Russia, when we do the railway, we don't connect the rails with each other. Like we leave some race for and temperature.
Well, you have to. So first of all, the old way of making train tracks was the tracks, there would be a little gap and they would be riveted together with bars across. But the problem with that, when the wheels are going over it, you hear it. It's like click, 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 noisy train. But for high-speed trains, it's going 300 kilometers an hour or something. You can't have that. It would not work. They have to be completely smooth. So there are expansion gaps, but those are sort of diagonal cuts lengthwise that are also very smooth. But for very long stretches, it's continuous welded track, which is a relatively newer technique. And the problem is that doing the welding is hard because there's a lot of iron. It's very thick. It's 100-meter long sections that is conducting heat away from the joint. So if you just tried to use a torch, an acetylene torch or something, to weld it together, it's impossible. It's too thick. It's too much mass. So when they're building new track, like they're putting in an entire new section of track, they have electric arc. It's like a big train car that follows along the track, and it's able to put enough energy in electrically. You have to get both ends of the rails, the ends of both pieces of rail completely molten as a liquid, and the gap filled in with liquid, and then have it cool and become one single piece all the way through, as if it had never been separate. Otherwise, it's not strong enough. It's not safe to have the trains going that, and it's not smooth enough. So, when they can have a giant machine, they do it that way. But when they're repairing sections, they use thermite. That's the current way that it's done. And it used to actually be that it was always done with thermite as the only practical way of getting enough heat in a concentrated place all at once to actually melt it all together. And I think it's sort of surprising, actually, that thermite welding it's a very widely used technique, even today, for situations where you need to have more heat more quickly than you can realistically deliver with torches or even electric sources. So it's used for, if you have a big ship that has a huge cast iron steering column or something like that that's cracked, they make giant thermite welds, or, thermite castings essentially, in place to repair big things like that. It's a very useful reaction, and quite old, 1800s when it was first discovered. The trick is it relies on aluminum, and aluminum was isolated fairly late in chemical history because it's quite difficult to isolate. Well, you need electricity actually to get it out of its ore. But once you have aluminum, you can use it as a reducing agent to turn lots of oxides back into their metals.
And the last question is about, as you said, as you said, aluminum and bromine reaction. So, why is how to be safe so relevant for the world?
Yes, well, that's the thing. It's used as a chemical demonstration because it's a very attractive demonstration. It's fairly easy to do. If you have bromine, bromine is a little hard to get, but if you have liquid bromine, you just drop aluminum foil in it and you get this beautiful spontaneous combustion. It's a demonstration of an electron, transfer sort of reaction. It illustrates an important sort of chemistry, but I don't know what the relevance is in the same way as, for example, the thermite reaction. I just told you a whole story about train track welding. It's very clear that chemical reaction has a very direct application. The hydrogen gas bubbles, it's very relevant to, this is something you read in the newspaper. It's fairly common. Some house blew up. Why did this house just blow up out of nowhere? It's always, I always thought that was sort of mysterious. Like, we have this gas. Where I live, people use propane as a heating source. And propane is particularly likely to do this because it's heavy and it accumulates in low areas in the buildings. And every year, sometime during the winter, there will be a newspaper article that talks about somebody's house blew up, somewhere in that area. And so I think this, that reaction, that's showing how pre-mixing of the fuel and the oxidizer makes the rate of the reaction much faster because it's limited only by the propagation rate of the reaction rather than the mixing rate. That's very relevant. People can understand But in the case of bromine and aluminum, I don't know. I can't think of anything. It took me, like for the hydrogen soap bubbles, it took about a year of thinking about it. Like I knew I wanted to write a column about this demonstration because it's a great demonstration. But my editor wouldn't let me write the column until I could tell him why should anybody care about this? You know, he's not a chemist. He doesn't care about that it, you know, whatever. So like he would not, I don't write the column anymore, but if I did, he wouldn't let me do the bromine reaction. And maybe in a year I'll figure it out. And I'll think, this is, okay, great, this is a model for understanding something. Don't know what it is yet.
Do you have experience for reaction with xenon tetrafluoride? It's very beautiful.
Which one?
Xenon tetrafluoride.
Xenon tetrafluoride. Is that what you're saying?
Sorry?
Sorry, what is the?
Xenon.
Xenon, yeah.
Tetrafluoride.
Uh-huh.
Any organic compounds.
I've never seen that reaction or that compound. I've heard about it, but I haven't seen it. You say it's a nice reaction? Really? I should look that up. Yeah, no, I have not seen that. That's an unusual compound. I mean, it's hard to make, I think.
Thank you for your presentation. That was absolutely amazing. As a teacher, I'm interested to know, is your approach in presenting chemical elements implemented in American schools? How do American children study them?
Yeah, so I've asked many students, high school students, what is their least favorite class in school? And more often than not, the answer is chemistry. Chemistry is I mean, the way that chemistry is taught in American schools makes students not like it. It's not like this at all, right? It's taught as memorize these elements. Here are the titration formulas. One student, actually my own son, when he was taking chemistry, the first week, the first homework assignment that he came back with was an assignment on the difference between precision and accuracy in measurements. So, you know, one is random fluctuation, the other is systematic error. This is what you start with the first week in teaching what could be the most dynamic and exciting subject in all of school. It's very badly taught. So I've been involved with several projects to try to improve that, but you know, but it really hasn't been improved. Now, ironically, actually, we can blame the Russians for the poor quality of science education in the US, and I'll tell you why. So I worked for a year and a half or so with a retired chemistry professor. He's in his 80s. He's written chemistry textbooks. He's an excellent educator, and he's been involved with chemical education in the US since the 1950s. And the way he describes it, chemical education in the US used to be quite good, and it involved much more this kind of stuff, like what are the elements, and chemicals, not just elements, where do they exist in the world, what is their importance, and maybe the first half of the year would be learning real things about real chemicals and how they work, and the practical things. And then there would be some of the more rigorous mathematics. But because of Sputnik, so, you know, Sputnik changed everything in the US because we had this idea we're so clever, you know, and then the Russians put a thing in orbit before us. And this was very upsetting, you know. And so everyone said, well, we have to improve science education. This is a disaster. The Russians have done this first. This is terrible. And one thing that was decided is we have to make education more rigorous, more formal, more math, more formulas. And so, you know, chemistry followed that. Like, no more talking about iron ore and where does it come from. What's some formulas? What are things we can put on a test? And what's some mathematics we can put into it? And the result over a few decades was that the subject has now become incredibly uninteresting to people, and they think it's just formulas. And it's lost which really are not useful to anybody who isn't, like if you're going to be a professional chemist, yes, you need to know these formulas, but you can learn them in a week in college. For the average high school student, it would be much more important for them to understand the significance of chemicals and how they work and how you evaluate is something dangerous or not. None of that is in the typical science classes because of the push to make everything quantitative and mathematical, which started with Sputnik. So, and everybody knows this. I think like there's many people in the professional educators who realize that this is broken, but it's very hard to fix. It's sort of institutional gridlock. It's hard to say, well, we should teach this differently, but then the students won't do as well on the test. The SAT, the standardized test, they won't get a good score. We have to teach them the way that they'll get a good score. And it's not. I don't know. Yeah. In other words, no, it's terrible in the U.S. is the short answer. It's terrible everywhere. I don't know any country where it's taught well. I guess I don't know in Russia how it's taught. If it's done better here. Awful. Yeah. Well, I spend a lot of time in China because the Chinese government has decided that their science education is awful and they should do it more like the Americans. They don't realize that. I don't know anybody that does it well. I think, and chemistry in particular. I don't know that. Physics, I think physics teaching is much better in some ways. And, math is better because math is actually math and you teach math and that's fine. But chemistry is not what it should be. It should be a very different subject.
Hello, my name is Lisa and I have one question, but for not all schools in Russia have tribal awful chemistry and biology lessons. I'm studying biology class in one school, and we have amazing lessons of chemistry and chemistry very much. It's very interesting. We're talking about.
So I'm guessing you have one teacher who is a very good teacher.
No, we have like 3 chemistry teachers. They're very good teachers.
Well, you're very lucky.
Yes, and I have a question. Today we were talking about like 3 topics. If we can call topics like about elements, molecules, and reactions. And we have 2 paper groups about elements and molecules.
And reactions. It's just the reactions is not in Russian yet.
I want to ask if you like to write reactions book. You have reactions book?
I have reactions book. I don't have it with me. I just gave away my copy. So it came out in English last year, and I hope. I hope that my Russian publisher will have it translated. It's sort of not under my control whether they decide to make a Russian edition of it or not. But yes, that was actually, when I was most of the way finished, when I had almost finished writing this book, which was 2009, I guess actually it would probably 2008, when I was still working on it, I thought, really there's 3 books, elements, molecules, and reactions. And it took 8 years to finish those 3, but now they're finished. And those 3 together, that's chemistry, right? I mean, you have elements, and out of elements you can make molecules, and then when you have molecules, you throw them at each other and you make reactions. That's chemistry. So the 3 together, they fit, and that's finished now. That's all of chemistry.
I was reading the book about elements in Russian, yes, in language, and it's very interesting. Thanks a lot for it.
Thank you. Okay, well, if there are no more questions, thank you for coming.